this is last week's discussion. So I will finish this shear stress, shear strain, the shear modulus, all of the information by, I hope today you can finish it. And maybe provide you with one example. But I think you need to check some exercise that I provide. Because I need to know like how difficult it is for you to solve the problem and which part that takes time. I haven't uploaded other video for the solving problem. I hope this week I can give you another video for the solutions. Because if I take all the solving problem in class, maybe just half the process. The other process more on the computations. I leave that to you. Okay? You can just focus on your calculator for calculation. But now, what I want to focus is, like if you remember learning the statics, the first thing you need to do is identifications, right? You need to draw the free body diagram, right? To draw all the forces that is important in this in problems, and then in mechanics of materials, the forces will be more elaborative, will be a little bit complicated because we will ask the some of the mechanics properties, okay, some of the mechanical properties, and then but the idea is still the same. You still need to draw the free body diagram at the beginning, okay, and then all the statics you did, like that is the first steps usually what you need to do, okay, for our course usually. And we learned the normal stress, right? The normal stress, and now we have the shear stress. Okay, the shear stress is when the force or the distribution of the force is on the plane. Okay, on the plane. If you have like this 3 dimensions, it's on the plane like that. And another one example or important thing is you can imagine like a scissors, and that's why it's V, like a scissors. Okay? Easy to remember, right? So scissors is involving the shear stress, right? And there are typically 2 types of shear. I think most of our course we will have. The first one is the single shear, and the second one is double shear. Let me go through the new page. This is just like just a more elaborate explanation on the single shear and double shear. So this is what we have here. So imagine you have some plates, okay, and then you have a bolt, okay. And this plate you can imagine this is like you can rotate, you can do from this bolt. So you have a rotation here. And now see the second picture. Okay. We have some body here. Okay. So maybe rod, okay, maybe rod, iron, or steel, and then we have some platform here. And still the same, they have bolts. Okay. And you can imagine that we can rotate. Okay. So in this case, we have 2 platforms, like a sandwich is the rod, like a sandwich. Right? Now, if we looking at how this, if we cut and see how the reactions, there's reaction force, we will have a reaction force which we call here is S1. You say like shear 1, okay? And here in the second one we have two shear. Here and here, S2 and S3. And that's why it's having 1, having 2. And if we cut and make a free body diagram, like we cut and then make a free body diagram, so we just take away one sample, okay? And this is what we have. We have P2, P3, the shear stress, okay? And then we have the P1 here, okay? Okay, that's for the free body diagrams. So from this pictures, this is actually what we did last time, but this is I think just a little bit review. So we could start from, this is for the first one, the single shear. So we always start with the statics. The sigma, the sum of the force, should be 0. So that's the statics rules, right? And we get the shear force or the shear stress equal P. And for the second picture, we have the P2 and plus P3 equal P. Okay? So from here, if we generate the idea, and because of the symmetry on the double shear, we could say that, oh, P2 and P3, we could say it's half of P, right? And then we can take the average. We can take the average for the shear stress. The shear stress is the shear force defined by the section of the area or area. Okay. Now the different, the single and then the double will be in this formula. Okay. So this is for the single shear. Let me write that for you so you can have a clear distinction between those two. So this will be the single shear. This is double shear. You will see like the differences between single and double, like if you solve some problems, it's based on the information you have. Or maybe the problem provides some pictures with some references, and then you need to know which part is single, which part is double. Well, sometimes, because this is using diameter, sometimes the formula can be used using the radius. So you just need to cancel this 4 if this is radius, right? It will be 2r, right? 2r, and the 2, 4 cancel, right? This is 2r, so this will be 1/2. It can be in the this is diameter, so dB is diameter, D is for diameter. But sometimes you can also write P over pi r squared. And this is for the single, and for double this is 2 pi r squared. Either way, it's the same thing. Either way, it's the same thing. Okay, now, this is all we talk on the average of the shear. There are other terms which we call the pure shear, And this is I will give to you briefly, because this is not really that applicable in a calculation, but this is important in the definition. So if we see some like a plate, okay. So imagine we have a plate, and then consider the plate like this one here. Like consider a thin plate. And then if we observe this plate, and we observe in a small area, like here, okay, we say we have like a small area A here. That is, we give the notations delta to denote that this is very small, and you need to be aware of when something or any symbols they mention about delta, they will relate this to calculus for infinite small numbers. Okay? So if we consider the horizontal sections on A, and then we consider there's some small shear, that is, we call the delta VP. That is a small distribution of shear on A. Okay, and then if we zoom in on this A, we have this kind of distribution, or this kind of shear in the delta X and delta Y. Okay? So if we take this away, actually we have shear on this delta X, okay, and shear on the delta Y. Okay? So that is in equilibrium. In equilibrium. So we call this equilibrium requirements for the shear. For shear stress. So it start like when you did statics, we start with the sum of the force need to be equal to 0. So we need to have the sum of the force on the x-axis. Okay. So if you want to make it in equilibrium, this shear here needs to be equally with this shear here to make it a 0 equilibrium. And shear that goes down here for the y is also getting shear on this part. Okay. Because if you look here, or if you imagine, I didn't bring the tools. If you imagine, if we have a shear going through here, if you imagine like a clay, or like Play-Doh, like a cube Play-Doh, if you put some force, you press or shear this part here, there will be some reactions here. Okay, if you put here, and maybe there will be some reactions that is going there and going down here. Okay, if we push the body. Okay, and this is, I think, very logical shear diagrams. And then, aside from this sum of the force, we need to sum for the moments. Sum for the moment. Let the moment at the at A. So mz at A. So the z is going to be here. The x, y, z is, so x, y, and z. Okay. And the moment according to that z-axis, and we are going to take the points perspective at A. So this will be equal. Let me write this is equal to 0, and then the shear Q is for the Q axis, which is the y, and then T delta y. Okay, T is the thickness. T is here, the thickness. T delta y, and then multiply with delta x minus the P and delta y. So the distance is just T, okay, and the delta here. Okay. And we could see the results that the shear on Q will be equal to the shear on P, and then we can say this is with the same symbol, okay. That is summarized in this the picture on the right side, which we call the pure shear. Okay. Okay, let me just emphasize what we did here. Okay, so the summary, for a quick summary. So shear stress on parallel force parallel phase are equal in magnitude and opposites in a sense. So the key important here is equal in magnitude. So parallel phase, okay, which means this one here. So the one that parallel here, parallel there, they are the same magnitude and opposite direction. Okay? So every time we talk on what is the pure shear or what is the shear on one element, we can just draw like a small element and take the shear like this. Okay. Okay. Okay, that's the and on opposites in a sense. And then one more thing, they need to point toward intersection. So what does that mean? It means that like this. So if this is going to be here, so there will be another one that will be going to be there. Okay. So it should be head to head like this, or tail to tail like that. Okay. This is just a definition on if really we need like a pure shear on one element. Okay, that's all the shear stress. Okay. Okay, let me take this a little bit down here. And maybe take this a little bit right. Okay, and also here. Okay, the point, okay, in our course, as I mentioned many times from the beginning, is you need to try some of the exercise. I think I give you the exercise for the statics, for the normal stress, and then the strain, the extensional strain. At least 3 kind of questions. At least try that out. Okay. The exercise. I will put another additional explanation on some problems too. I think related to the shear stress. Okay. And aside from the shear stress, we have this is for the shear strain. Shear strain. I mentioned a little bit about shear strain. So let's see that we have a cube, like any material, any element. Okay, and let's say it's like a perfect cube, like perfect cube. If we push and make it a deform, okay, make it a deform, and let's look at this second picture. So we take the shear, and we push that way, okay, and it's also changed the shape here, which means that the angle that previously is a perfect cube, which has the angle of pi/2, now it is changing. It's become the new theta. Okay. Okay. Now we have the gamma. This is the how much this line moves, okay, after we apply the force. Okay. And then we have the delta here. This is the distance, the new distance for this part. So if we take points on this one here, every point, not every point, some of the points from the cube, they move. Okay, they move here, and this move there, okay, and this move this much, the delta, okay. Delta S. Let me zoom in to make it clear. Okay. So this asterisk means this is the new point after applying the force. Okay. Now the shear strain we call with the gamma. So shear strain, let's say at A, according to the picture, is defined as the change in angle between two, let me take two originally perpendicular line segments. Or if this is too complicated, you need just to remember that the shear strain is equal pi/2 minus the angle that is changing. So the pi over 2 means that this is the original angle, let's say at A at some point before deformation, and the angle, the theta with the asterisk, this is the angle after deforms. And as we mentioned, when we have the small angle approximations, we could also, let me write here, small, although it's not really popular in most of the questions, but this can be done with a small angle approximations. If you remember what the small angle approximation means, this means that we can take the tangent of some angle is equal to that angle itself, and sine also the same thing, because sine and tangent, they are proportionally the same. Okay, this is what we call the small angle approximations. And then we could take the angle, the gamma. This is pi over 2 minus theta asterisk. This can be approximated using tangent pi over 2. And then from the picture, we know the tangent itself, okay, from here. This is from this triangle. So the delta and L. Okay. So this is delta S over LS. Okay. And this is valid because mostly the shear strain, the angle, is really small. Okay. Of course, you need to imagine not like if you have like a clay and then you push and then there's a shear, that will be very big angle. But if you think like a structure, like you have a steel, like a buildings, you will be having a small angle that will be deformed. Okay. So I think what I need to emphasize this scan. I think aside from practice, you need to also prepare some I think good notes. I mean your own notes. Because I think for the exam, I will give you opportunity to use one paper for notes. But still, I think still difficult if you are not sure how to use it. So please make sure when you try to take notes, make sure you emphasize the important one. I think I will give you I think example about the shear stress, okay, and perhaps shear strain if we have time. But I think shear stress, but I think not 100% solution, but I'm trying to give you the idea, okay, and then after that we can move to the design, okay, the design or engineering design. Okay, so this is shear stress, shear strain, okay, as introductions. Oh, before that, a little bit on the material properties. Just a quick notes here. So material properties in shear. So remember, if you have a tensile or a normal stress, you have the modulus, right? The modulus of elasticity, right? Or Young's modulus, right? So in shear, we call G the shear modulus, and based on the Hooke's law, it's actually just the slope, because it's a slope, very similar to the normal stress. The shear equal the modulus multiplied with the strain. Okay. You could imagine also this can be written as G, the shear stress over the strain. Okay. It's the slope. Okay. The G is the slope of the still variable. Okay. You remember we have tensile stress like that. The elastic region or the elastic property is the modulus, right? And this also happens if we take the shear, and we call the modulus is G, the shear modulus. And then later, if we have time, well, maybe we can show we can relate the G with E. That is, let me write the formula first. Okay. G is equal to E over 2 multiply 1 plus V. There is some formula to combine these two together, G and E, but I will leave that for a later discussion. Let me just write this for now. Then we can rewrite the shear modulus equal to E over, and I think this is acceptable because G and E are the same modulus and they need to be proportional. Okay? They need to be at the same ratio. Okay? Here there will be some key factors from the shear that makes G and E different. Okay? There are some factors here. Okay, let me give you example on the shear stress. That is for later, of course. This will be okay. So since I forgot to write the questions, let me just draw for very quick here. So let me take this. There's a wall. There's a pin. And then there's another pin going around here. Okay. Okay, and then we have another pin here. And then that's a D picture. And let's say we have A, and then B, and then C. Okay, and then we apply the force around here. This will be 50 kilonewton. And that describe the distance from A to this force. Oh, maybe too close. Maybe if this is 4, maybe this is 3. Maybe around here. This is 2 meter. And this is 4 meter. Okay. And for the diagonal sides, it will be in a proportion with the Pythagorean 3, 4, 5, the ratio. Okay, and then it says that for pin A, this will be this type of pin. And for pin B, this will be this type of pin. The questions, let me write here. Find the average shear stress on the 20 millimeter pins at A. So the 20 millimeter pins is at A. And B. B also 20 millimeter pins. So the red color is the pin. Okay, this is the pin. Is it or diameter? Okay. So diameter is 20 millimeter. 20 millimeter. So find the average shear stress on the pins at A and B for the given load. The given load is 50 kilonewton. So we have 2 pins. Let's just see and observe the pins first. Pins at A and pins at B. Which one is single? I'm not asking you. Which one is single from this picture? Which one is the single? The right one, right? This is single. This is double. Okay. I hope you can get the idea. So let me write. This is the single shear. This is double. Okay. Okay. And then what we want to find is the shear in this space. But can we do that directly? Can we do that directly? Can we find the shear here from all this information we have? Not yet, right? What's missing?
Find the support at the edge.
Yes, which means if we look at the macro level from the picture, we see there is a load. Okay, the information is a load, but we need to know what kind of external force that might also affect the shear, right? And how does we compute that? We see that we still have this member, right? And that's the first thing. So this is the statics. Okay? So you draw the free body diagram, finding the other force here. Okay? And then after that, we cut open the A and B, and then calculate each shear. Okay? Let me help you with the diagram. So first step, always start with the free body diagram. And this principle will stay as it is every time we solve most of the problem we have, okay, in mechanics. So let me just take the AB. Okay, let me just take the AB. So let me draw AB. Okay. So this is A, B. So in A, we have a 50 kilonewtons, and we have pins A. Imagine there will be reactions, right? Will be reactions. What kind of reactions? Imagine that A can move like this, right? So there will be only X and Y, right? Force, reaction force. There will be no moment because it can move freely, right? It can rotate freely. And how we decide right side, left side, down, up, anything. If the calculations negative, you draw the wrong direction. But this is okay, same calculation, okay? So, I will just give you the correct one. It's going to the left. And this will be going to the up the top. So let's name it AX, AY, and then giving the 50 kilonewton here. And then we have this part here. This is the force that is on the member BC, okay? The truss BC. So let's say we have FBC. Of course, this is because we have the triangle, the 3, 4, 5. We can make out the sine and cosine components, right? From the 3, 4, 5. So we can have this component here. This is FBC, 4 over 5. And this one is 3 over 5. Right, sine 4, 5, yeah. Okay, what's next? Second, go for the equilibrium. We can take the equilibrium and we can start with the sigma F equals 0 or sigma moment. And I will suggest start always from the moment. Okay, start always from the moment. So start from the moment. Why? If you look here, if you want to calculate the moment, which means that in every member here, the positions, what's the moment is? The moment is the force multiplied the distance, right? The force that is perpendicular, right? So if we want to know, for example, what point do you want to take? Is it A or B? Let me name here. I forgot to name. This is A, this is B. Which point you want to take the moment, A or B? It can be both, but I want to know from your perspective, which one?
I think both are fine in this case.
Yes, both are fine. Okay? But if we, for example, if we take A, which means that all this AX, AY, we don't really need the calculations. So every force will multiply with the distance for every perpendicular force, and we will get the FBC, right? And either way, if we take in B perspective, we will get AY. Okay, so either way, it's okay. So let's take a break for a while. So first, if you see the free body diagram, the first step, free body diagram. The second step, write the equilibrium, and starting with the moment. Okay. For my solution, I will take the moment at A. So everything will be coupled to this A. So 50 coupled here, and then this 4/5 FBC coupled going there. Okay. So sigma moment at A is equal 0, and is equal to, I will take the clockwise as a positive. Okay. Actually, this positive or counter positive the same as long as you're consistent, because every time you have like this, the other one is the opposite, right? Minus positive should be the same. But if you want to like make sure and confirm, you can try just make your assumption first. Okay, every time we have clockwise positive and write this. Okay. But if you're already familiar, I think you can just go compute. Okay. So negative 50, and this was the 2 meters, right? We have 2 meters, and we have this is another 4. So this is 4 meters. So negative 50 multiplied by 2, and then FBC, it's oh, it's supposed to be positive, sorry. And then minus FBC. So FBC 405 is equal 100. So FBC, if you calculate using your calculator, oh, multiply by 6, sorry, I forgot the distance. So this is 24, right? Okay, and then FBC is 500 divided by 24. This is around, I already calculated before, 20.83 kilonewton. Okay. So you get FBC. Okay. And then we get the FBC. So we have all these components. We know the force. And then we take the sigma force equals 0 for x and 1. And we can calculate these two, the AX and A1. So we take the sigma F equals 0. So AX is equal to 3/5 FBC. FBC is 20.83. This will equal to, I also count this, is 12.5 kilonewton. And then we take the y-axis, and AY plus 4/5 FBC, FBC is 20.83, is equal 50 kilonewton. And we can compute this and determine AY is 33.333, let me just make 4 kilonewton. Okay, so all the reaction force. So we have all the reaction force. Okay. So from the body diagram, the free body diagram, we have all the external force we need. Okay. We have. Oh, I forgot. Because we have AX and AY, then we can calculate the magnitude of the resultant of AX and AY. Okay. So let me write here that the resultant of the force, like a factors, if you remember the factors, so we can just take the square root and take these two numbers in squared. And you can also check with your calculator. This is around 35,000 Newton. So this is force at A. So this is, we can also say, this is the shear force at A. This is the one that we need to define and take this compute the stress. Okay, so the force at A, and what is the force at B? The force at B is this, to 20,800 Newton or 20.83 kilometers. Or 2083 Newton. Okay. And now the pins, right? The pins at A and B has the same diameter. Their diameter is 20 milli, so we can compute the area, right? So basically, let me just like this give you the informations. The radius is 20 millimeter or 20 millimeter. So the area, if you want to use the radius, is 10 squared or 3 millimeters squared. Okay, the area, both of the pins. And remember, for the single shear, we take the force, the shear force, divided by the area or the pi r squared. Let me just write A to make it easy. And for double shear, we take V over 2A. I think it's better to write, right? Because A, you can write with the diameter, you can write with the radius. So I'm trying to simplify all the formula in the textbook. Okay, single shear, double shear. And then, for A, we can just take the double shear. Okay, we take the double shear. So let me write here, maybe down here. So let me write pin at A. Maybe just write the formula. So this will be VA divided by the double shear is 2 multiplied with the area, right? This A is different. Okay? A for pin A and A for area. So we can write the shear at A is 35,606 Newton. And then the area is 314. Okay. 2 multiplied by 314.16 millimeters squared. Okay. You can compute, and remember, Newton over millimeter squared is megapascal. Megapascal. You can check Newton over Newton over meter squared is pascal. Newton over millimeter squared is megapascal. It will be millions. Right? It will be millions. Okay? And it will be very important conversions in material science or in mechanicals. Because we usually deal with a big structure that is on megapascal or gigapascal. But if you read the standards, like mostly they will mention the magnitude in the scale of the megapascal. So this will equal to 56.67 megapascal. And pin at B let me precise a little bit and take here. So pin at B is just a single shear, just a normal. So VB and then just area. This will be 20,330 Newton, and this is the same but not multiplied with 2. This will be 66.3 megapascal. And this is the answers that we are looking for. Okay. And sometimes, although the key concept will be the same every question, usually there will be like some accessories. So the key concept is like you draw the free body diagram, and then try to find the external force. That is, for most of the case, that is the first thing you need to do. Okay? The third one, if there is some, let's say, accessory, additional, for example, additional like this, oh, shear at pin A, pin B, or that's one, the one that we need to cut and see the internal force. Or if they mention something like steel with some, the steel is very precise, and they give the name like A16 steel, means that the steel has some property, right? And usually that will relate to the modulus of elastic. Okay? Usually they will relate. And what's modulus elastic? It will relate to stress and strain. Okay? Stress and strain. Okay? We will, and I think if we have time, maybe I will add in an additional video probably. If we have. Okay. But if we have time in class, I think I will go to those kind of examples. Okay. I think let me give you another example related to strain and the Poisson ratio. We mentioned the Poisson ratio, okay, I think last week. Let me give you an example on that. I forgot to give last week, so let me give you now. I hope everyone finished the notes. So example, strain and Poisson ratio. Let me give you the quick example here. Let's say we have a pin, and let's say this is like a cable going over there, and then this is another pin, okay, and then it have another connections. It has another pin here. Okay, and imagine we are going to move this pin, move here. Okay, so there will be, so the wire is kind of stretching or extension. There's some extensional strain. Okay, so let me draw this illustration how it looks like. Maybe not really good, maybe with the same color. So this is just a small strain. This is if we move, okay, if we move, and we have now some angle here, really small, 5 degrees. and we have a force that is, let's say, P. And then the cable or the wire is 1000 millimeter. And the height for this specimen or materials is 800 millimeter. And the distance between the pin, the distance is 600 millimeter. And let's name the point. Let's say it's A, B, and C. So the question or the goal is the flexible, let me write, flexible cable AB is attached to rigid beam. Usually this is to simplify the question. So it just says rigid beam, which means that the small angle approximation will apply. And a load P is applied. The bar displaces 5 degrees as in the picture. I mean the bar is moving, rotate around 5 degrees. The questions: find normal strain in AB. Oh, this is not yet Poisson ratio, but this maybe later. Okay, the second one. So remember, when you talk about strain, what does that mean? It means there will be a deformation. What's deformations? There will be some elongations or stretch or extension of strain. So imagine you pull this cable. The cable will stretch, it will stretch. And the question is asking the strain for this cable AB, the normal strain, which means we need to find the strain that is applied in the axis. Okay. Now, how do we deal with this? Any idea? Any idea how do we find? So first, before we find the normal strain, the definition of the strain is the elongated final form minus the original length divided by the original length, right? So we need to know, if we stretch the cable, how much is it? Can we find that? Can we find this from the picture? Can we find? So if this is the cable, okay, and this is the final product. So let's take line from this, and this is the new triangle. Okay. Look at the new triangle. Can we find something from the new triangle?
Can maybe rule of sine? Laws of sine or cosine?
Yes, law of cosine. So you need to review a little bit of trigonometry, okay? Okay. So here, let me draw. So if we take, so sometimes we need to use this also. So this is a new triangle. So let me draw in a new picture. So let's say this is we have the bottom still the same. And this 800, I forgot to mention, this 800 is actually the length of bar. Okay, so we could take this, and also why I'm sure that it's still 800 here, because it's mentioned as a rigid beam. So every time you hear or you find in the questions rigid, it means that it will stay, the length will stay, not stretch. Okay? Rigid beam. So it will be still 800. Okay, let me write here, because of rigidity or rigid beam. Okay, so 600, 800, and we have the degree. This is 5-degree displacement, so 90 plus 5, right? So we can take this 95 degree, and let's rewrite the law of cosine. And anyone remember? Law of cosine. So if we have a triangle, let's say if the angle is A, not B, maybe it's easy for C, and this is B, and this is A, B, C. The C squared is equal A squared plus B squared minus 2AB cosine C. Okay, so we can take C squared and take the 600 squared plus 800 squared minus 2, multiply 600, 800, cosine 95. And then you can get the C. Okay. And this will be, let's just say, approximately 1041 millimeter. It's I rounded the numbers. Okay, now we have 1041. We have original length 1000. So there will be additional length delta F is 41 millimeter. So it's really small compared with the 1000, right? It's small. So we can say the delta of the length is 41 millimeter. So the strain of the cable AB is delta L over L, or 41 over 1000. And this is equal to 0.041 millimeter per millimeter. Okay. Although the strain is that it doesn't have any dimension, well, usually we write the unit as length over length. For the Poisson ratio, I will keep that for next week, I think, if we have time. Okay, any questions first? Any question? So this is not yet Poisson's ratio. Okay. So sometimes you need to take some using geometrical perspective. In the trigonometry, some basic trigonometry from math to simplify it. And most of the problems, if you see some of the examples, they are simplified. Like for example, the rigid beam and the small angle. Okay? So the calculation should be simplified. Of course, in the real world, not that simple, but this is just for observations, okay, for analysis. Okay, now the next sections, I want to introduce you to just the basic on the engineering design. Engineering design. Okay. If you maybe not seeing clearly, let me know. Okay. So engineering design, as in mechanical property, which means we are going to design some either some equipment or anything that related to the product. That, for example, your water bottle. Perhaps they need to make the design to be lightweight, easy to carry, right? Easy to carry, but it still has some good mechanical. Like if it drops, it doesn't break, right? So that's some requirement. So you need to know, like the last week or maybe last 2 weeks, we discussed on the mechanical property. We have the strength, right? We have the yield strength, yield stress, right? The stress, and how much we need to take that as a limit is important, and that is part of the engineering design. Okay. So let me start with, and you will see what is the important part on this design. So this is a fundamental to design objects that support or transmit load. And the design itself involves selecting materials, okay, material selection. Material selections, and apply the mechanics principle. The idea is, the conclusion, so that no failure, okay, no failure occurs. That's the idea. Occurs under under the prescribed loading conditions. For example, your elevator. Usually you see the numbers or maybe some informations like 10 people or 12 people. That means that's the average weight that the elevator can hold. For example, if it say 10 and maybe you put 11, can the elevator still run? Sometimes they still, right? Because it depends on the weight. But maybe if you increase more, maybe 13, maybe it has the alarm, right? And maybe you hear the sound. But did the elevator break? Break or no? No, right? You still have a chance to go up. So that means there is a stress that makes elevator breaks directly, and there will be some like engineering principle that we need to count, and we can make sure, okay, this is safe. And that is what we call the safety factor. Okay, the safety factor. So need safety factor. So the safety factor or factor of safety, well, let me just ask F. Okay, the safety factor is equal the failure load divided by allowable load, and you will have some number. He will have some number, some ratio. So of course, the safety factor from this stress, because the failure load is practically higher than allowable load, right? So the ratio will start from 1 and greater than 1. The safety factor will always start greater than 1. Of course, there will be some factors, okay, aside from the loads, but that is not really in our details. But let me just show you what the other factors is. Like some factors determining SF. The first one is the importance of failure. What type of failure? For example, if the failure, for example, like this building, maybe the failure is one of the pillars. It means that it will affect the other part, right? It means that it can increase the safety factor. We need to increase the safety factor on that part. And then the second one, maybe accessibility. Accessibility for inspection or repair. Imagine that maybe the equipment is not easy to be accessed or to be inspected. Then we need to make sure that it is really, really good. So that's why we need to make the safety factor as high as possible, if that's happened, right? The third one is the nature of the possible failure. What kind of failure we have? Is it like a ductile failure, like it's deformed and then fail, or it's a brittle? So it depends also on material, design, and the possibility of failure. And the fourth one, also the cost. Do you have the budget? Okay. So like for example, like the water bottle, maybe we don't really need like really high. So that's why we use polymer, okay, like a poly PET or any polymer that is quite. It's supposed to be mechanically stable, but not that really strong like steel, for example. But in our course, of course, this is not really in our like in a computational problem, but mostly our problem will depend on this, the failure and the allowable load. Okay, aside from this load, we can also write the safety factor in terms of the yield strength. So not the failure, but the yield when it's deformed plastically. So yield strength over allowable stress. We could also write this safety factor as this. So we could write the stress allowable, let me write allow for allowable, equal to the sigma yield, or usually yield using that, over safety factor, or the shear allowable Of course, this is for axial deformation. Axial deformation this is for tensile, this is for the shear. Okay. I think we can have a example. Show tree. Okay. Let me draw some example for the safety factor. What kind of questions we have? Let me quickly draw. So we have a pin. And then there will be another pin here. And then another pin over there. So the same beam. And this is the end of the beam. Take the A, B, C, and D. It's actually 90 degree. So forgive me if this is not 90 degree. It is supposed to be 90 degree. This is 3, 4, 5. There is a force that on point C that is 22 kilonewton. And then there is a distance. This is 1.2 meter, and that one is 1.8. I think I draw not really in proportion. Okay, let me write the questions. Equilibrium of beam AC can be used, or not this question, sorry. Beam AC supported by pin at A and rectangular tension bar BD. Okay. And the pin A, I forgot to mention, the pin A is having this kind of connection. And then pin at B is having this kind of connection. Okay. So you know that's double and single, right? And then tension bar. Maybe just write the question first, and then I think we can finished on Friday. Tension bar is made with steel with a sigma yield 250 megapascal and pins at A and B have a shear yield at 330 megapascal. So the bar for the tension bar is made with a steel that has sigma yield 250 megapascal, and the pins have a shear yield at 330 megapascal. The design load is P equal, I think already in the picture, 22 kilonewton. And then the safety factor is 3. If width of bar BD or bar BD, we call W 50 millimeter. Determine thickness that's A, the second one, and determine the required diameters at A and B. So the width for BD is here. This one shows the width. Okay. The one you're looking for is for AC. Okay, for AC. The required thickness AC. Okay, AC. So this is the thickness. Oh, no. Same BD. It's the thickness and width. So this is BD. Not the AC, sorry. So BD is rectangular. BD is rectangular. BD is rectangular. Oh, sorry. BD is rectangular. Rectangular tension bar. Okay, that's the question. I think we are going to discuss this next Friday. Okay. Okay, that's it. So the double is the width, the thickness is the, I think for that side.